Daggone it. All right, well, welcome back. I know you probably had a wonderful, restful break and probably got so bored, you're like, I need to get my chemistry fix. No. And that's okay. I'm here to help you. And let me also say that this semester is a lot more interesting than last semester. What I mean by that is last semester you were learning the basics, like on how to write a chemical formula, learning your 52 elements, names and symbols, learning the polyatomics, all that other fun stuff. Well, this semester is more math than it is concepts. So if you like the math, then you should do well. Now, what we're doing today is simply just adding. So if you can add, you're in pretty good shape. But this unit, we're going to be talking about bouncing chemical equations, and then later on you'll be predicting the chemical reaction types. But first of all, let's go ahead and talk about what a chemical reaction actually is, since we haven't really done anything with chemical reactions yet. But if I take two things, pour them together, and nothing happens, what has happened? Nothing. Very good. So no reaction. Nothing's taken place. However, if I take two things and pour it together, and one of these four things occurs, then we have evidence for a chemical reaction taking place. And don't just think, just because I put two things together, they're automatically going to react with each other. It's just like putting you with another person. Doesn't automatically mean that you're going to like that person, react with that person. You just might look at them and walk away. That's fine. Okay? Just like in chemistry, just like with you. You don't necessarily like or want to react with somebody, all right, or something in particular. However, it's a little more consistent here with chemistry. So if I have the release of a gas, when I mix those two things together, I have evidence for a chemical reaction. If you form a colored gas, anything other than clear, run. Okay? Seriously, because colored gases are toxic. Doesn't matter if it's black, white, brown, green. Those are probably the colors I don't want to see form and coming toward me. All right, those are toxic, so get away. Now, that doesn't mean just because it's a clear gas that it's safe. We just happen to be enjoying these clear gases right now. I'm okay. Okay, but there are some others like methane. I know there's probably a pocket of methane somewhere over there by Connor and whatnot. But hey, what? No. You know what methane is, right?
Yeah.
Natural gas. Which also something that you produce.
I know.
Oh, okay. All right. Color change. So if the substance changes a different color, you have evidence for a chemical reaction. The formation of a precipitate. This we're going to talk a little more about next week when we actually focus on that. So don't get too hung up on that just yet. And then if there's a change in heat and light. Now, who can give me an example of a change in heat and light? Explosion, fire, things like that. Okay? But they don't necessarily have to do that. A light bulb is a great example. There's a reaction going on there. Writing a chemical equation. You're going to learn about the things on the left side of the equation and the things on the right side. And some of you may have heard of this before, I hope. I hope this isn't the first time you've heard this. But the things on the left side of the equation are called your reactants, the things that we start with. And even though we have a plus sign here, I don't have to write the propane first. As long as it's on the correct side of the arrow, I could have written this as oxygen and propane. But I wouldn't put the propane or oxygen on the right side. The right side are the things that are produced, or the things that we finish with at the end. Those are called products. So the things on the left side, those are your reactants. Things on the right side, those are your products. It's kind of like a tombstone, all right? So this side represents the year you're born. This side represents the year you die. The dash in the middle is your life, all right? So there's a lot going on between here and here. That's what the arrow is representing. We're not going to focus on that. We might touch on it a little bit in AP, but all you really care about is the things that we start with and the things that we finish with. So you can treat that arrow as an equal sign, because we want to make sure that we have the same number of atoms on both sides and same types on both sides. All right, on the next page, you'll notice that there's a legend here. And again, it just helps to explain what some of these things are. So again, the plus just means and. The arrow means it yields or produces, and always our arrow will point to the right. when we work with these. You might see these little subscripts on some of the chemical reactions, not all of them. But if you do, then this helps represent a solid, that represents a liquid, that represents a gas. And aqueous we'll talk about a little bit later on. I don't want you getting too worried about that. The double arrow represents a reversible reaction where you can take the stuff that you start with and form products, and then once you have those products, it forms the reactants. The reality is the majority of the reactions that take place in the universe are these type of reactions, reversible, but we won't be doing any of them this year. Okay. In AP we talk about that a lot, but this year we don't even, well, we'll touch about it a little bit. And NR means no reaction, nothing happened when you mix the two together. And so in some cases you might have that. The symbols here, go ahead and get the blanks. I just talked about them up there. So you got gas and solid. All right. And then bouncing equations. We talked about this earlier on in the year where it says that matter cannot be created nor destroyed. So again, everything that we're working with in chemistry has already been made for us. Okay, like some of the atoms in your water bottle. Okay, those are billions of years old. They're as old as the universe is being made. So when you're drinking that water, you're actually drinking billion or 5 billion year old water, and that's okay. It's just being rearranged a little bit. The atoms are the same, they just combine and form different things. Okay. Thinking about what I was 50 years ago, I wasn't born yet. I don't know. Okay, I don't know where these atoms were at. I don't really care. I'm just glad they formed the way that they have right now. Okay, so when we think about atoms, they are old, so they're not being created or destroyed. They're just being rearranged, which is kind of neat. All right, when we talk about balancing equations, and here's a real brief introduction. If I look at this equation here, this chemical reaction where we have reactants, the arrow, and then the product. I have 2 hydrogens on this side, 2 chlorines on this side, but how many hydrogens do I have on the right side? 1 and 1 chlorine. So we don't have the same number of atoms on both sides. So what you're going to do today is you're actually going to balance these out by putting numbers in front. So if you have the equation already written for you, what I don't want you to do is change by putting additional subscripts in there. Don't go, oh yeah, I'm just going to make that H2Cl2. Don't do that. Put the 2 in front. What that means is now I have 2 HCl's. What are my numbers in front of the hydrogen and chlorines? 1s. They're understood. You don't necessarily have to write a 1 there, but if you do, make sure you clarify it somehow, some way. But normally we don't write 1s. Especially like here, we actually have H1Cl1, but we don't put the 1s because they are understood. But if you have a number other than 1, make sure you put it in front. And that represents how many of those molecules or atoms or compounds we have. Okay. And we don't want to have coefficients that are fractional. So we always want to make sure that they're whole numbers. And then the last thing is, once we finish balancing the equation, we want it to be the whole or the smallest whole number ratio, and we'll do that in our examples here. Then the next couple pages, up to page 7, it's all that, and I'm going to do those, or actually talk about that in the notes on the practice problems. Okay. So I'm going to turn the lights on. Keep your notes open to the bottom of page 7. Yeah, Kaylee. The 1/2, that is a fractional coefficient that some of you might have learned in junior high. It's okay, but make sure that you get rid of the fraction where to go here. So if you have a 1/2 here, then multiply everybody by whatever's on the bottom to get 2, or whole numbers. So when you finish, there should not be any fractions as coefficients. We always want whole numbers there. And yeah, the way I'm going to show you today, there is more than one way of balancing these equations, and I don't care what way you use, I'm just going to show you one of the most simplistic ways. All right, so let's turn the lights on. All right, so looking at the bottom of page 7, and the way that the practice problem is written out, this is how we're going to work these out tomorrow. the way your homework's going to look today is how they look on the back of page, or on page 8. So you'll have the balanced equation already written out. I'm sorry, you'll have the formulas written out for you. You just have to put the coefficients in front. So what I'm showing you today is kind of a little segue into what we're going to do tomorrow. We'll do more of it tomorrow or the next time that we meet. But also make sure that if you don't know your 52 elements, names and symbols, your polyatomics, how to write formulas that are balanced correctly, do that tonight. Yeah. All right. So number 1, it says write and balance the equation for the reaction of sodium and water to produce sodium hydroxide and hydrogen gas. So how do I represent sodium? Na, good. How do I represent water?
H2O.
Good. And sodium hydroxide. What's hydroxide? What are your 10 polys?
OH.
OH, good.
IO.
And the sodium has what charge? +1. Hydroxide is -1?
Yeah.
So that's balanced as written. And then hydrogen gas. How do I write hydrogen gas? H2. In other words, if it ends in gen or ine, I-N-E, then when it's standing by itself, it's diatomic. So nitrogen, hydrogen, oxygen, fluorine, chlorine, bromine, and iodine. So if they end in these, and it's the only type of element, okay, then we have to double it up. If it's just something like sodium, well, that doesn't end in gen or ine, so we leave it by itself. Okay. All right. So now that we have the basic down, again, this is the type that I like showing everybody. It's probably the easiest method. It's called the inventory method. So what you do is you take inventory of each of the elements that are present. So write a representative of each element that's shown there. And on the left side, how many sodiums do we have?
1.
1, good. How many hydrogens? 2. How many oxygen? 1, okay. Then we'll try to keep it in the same order on the other side. And oxygen. So how many sodiums do we have on the right side? 1. How many hydrogen? 3, very good. Oxygen? 1. When those numbers are the same, your equation's balanced. Okay. So, is this balanced? No. Okay. So the sodium we're going to leave alone for now. We'll skip it since it's the same. The hydrogen, we have 2 on this side, 3 on this side, but what's weird is we actually have hydrogen in 2 of the things. Over here we have hydrogen in 1. So what I'm going to try to do is realize I have an even number of hydrogens on this side. No matter what coefficient I put in front of the hydrogen here, will that give me an odd number ever? Never, as long as we're using whole numbers. So knowing that this will always have an even value, I want to have an even value of hydrogens. So if I do this, how many hydrogens do I have on the right side now? 4. Okay. In other words, 2 times 1 plus the 2 gives me 4. By putting that 2 there, that also changes the sodium and the oxygen. So how many sodiums do I now have? And how many oxygen? 2. Okay, so let's balance out the sodium. Put 2 in front of that. And how can I get 4 hydrogen on the left side? Put a 2 in front of there. Good. And that now changes my oxygen to 2 as well. Okay. Whoops, sorry, I can't. I just rewrote the same number there. So I have 4 hydrogens, 2 times 2. Is this balanced?
Yes.
Yeah. Okay, possibly. Good. If I can add these values correctly. Now, you'll also notice that I like to underline my coefficients. I do that on purpose because later on we're going to have numbers like that. Okay? And what I don't want to do is mistake that for an oxygen. So if I put the line underneath it, at least it'll help me see that that's a number, not an element. Now, what is the coefficient for this? It's 1. Okay. So if we had, and if you want to, that's fine, put a 1 there. Can I simplify this any further down? In other words, do I have the smallest whole number ratio?
Yeah.
Yes. So we're good. We're balanced. Okay. Number 2, it says write and balance the equation for the formation of magnesium nitride from its elements. So we don't know what we're starting with initially, but we do know what we're finishing with, magnesium nitride. Okay. Now, we have a compound that has magnesium, which is a what, metal or non-metal?
Metal.
It's a metal, and nitrogen is a,
Gas.
well, they're together.
No, just kidding.
Is it a metal or a non-metal?
Non-metal.
Non-metal. So a metal with a non-metal is what kind of compound?
Ionic.
Ionic, very good. So we want to balance the charges. So what's the charge on magnesium?
Positive?
Positive 2. And again, you get that from your periodic table. And the charge on nitrogen is so obviously negative.
Negative.
-3, good. Does that equal 0?
No.
No, so we need to multiply this by 3 and this by 2. Okay. So tomorrow, you'll get to do that. Today you won't. We're just throwing this out there to make it fun. So it says write and balance the equation for the formation of magnesium nitride from its elements. So what makes up magnesium nitride? Magnesium and do I leave it like that?
No.
Because nitrogen, diatomic.
So you just add a 3 in front of the energy?
I do a what?
You just add a 3 in front of the energy?
I don't know, let's see. So magnesium, we have 1 of those. Nitrogen, we have 2 of those. How many magnesiums do we have on this side?
3.
And nitrogen, we have 2. So we need to do what again, Kaylee?
Put a 3 in front of the energy?
There you go. And now we're balanced. Okay. Now, the reason why this 2 is here as well as here is not because I got it from here. We have 2 here because the algebraic sum needs 2. This is because that's the way nature made it. Okay. All right, let me give you some more examples. We're not going to do the ones on the back. This is your homework, this pack, or this sheet. All right, so I have 4 practice problems on here. Let's do those. And they're a little more interesting than... All right, so looking at Roman numeral number 1 here. All right. So we have the aluminum chloride, and it's reacting with barium nitrate to form barium chloride and aluminum nitrate. Okay? So that's a little bit more interesting than what we've been working with. So again, let's go ahead and get a representative of each element. So I've got aluminum, chlorine, barium, nitrogen, and oxygen, right? Oh, right, small. Yeah, good call. Thank you.
Yeah, you might want to give us more room next time. Maybe.
I'll try to work on that. Use the margins. You can use the margins as well. All right, so aluminum. How many aluminums do we have on the left? 1. How many chlorines?
3.
How many barium? How many nitrogen? 2. Very good. 1 times 2. Okay. How many oxygen?
6.
Very good. Let's keep it in the same order. So aluminum, chlorine, barium, nitrogen, and oxygen. So how many aluminums?
1.
How many chlorine?
2.
2. Barium?
1.
Nitrogen?
3.
3. Oxygen?
9.
9. Everybody see that? Are we balanced? No way. Now sometimes it'll be balanced as written, okay? But not this. Psh, no way. All right. Well, the aluminums look good, so let's skip it. Go down to the chlorines. We've got 3 on the left side, 2 on the right, and the chlorines are here and here. So how can we get the same number on both sides?
2 on the right.
2 over here, I'm hearing?
No. It's 2 on the right.
Yeah, it's 2 over there.
How about we put a
Oh, yeah.
2 there, like you said, and a 3 there? So let's refresh our inventory here. So we have how many aluminums? 2. How many chlorines? 6. Good. Okay. And then how many bariums? 3. How many chlorines? 6. Good, okay. So our aluminum's changed, our chlorines are good, our bariums aren't. Let's get the aluminums to be the same. How can I get 2 aluminums on the right? Or 2 there, good. So now how many nitrogen do I have? 1 times 3 times 2 is 6, good. How many oxygen do I now have? 18. 3 times 3 times 2 is 18, good. Alrighty. The aluminums are good, the chlorines are good. Oh, barium. So how can I get 3 barium on the left? 3 there. And how many nitrogen do I now have? 1 times 2 times 3 is 6. And how many oxygen? And that's a 2 there. 18. 3 times 2 times 3 is 18. How's that looking? Pretty good. Now, always do a final check. See if these can be reduced down any further. Can they? No. So we're done.
Mr. Craig.
Yeah.
So you're saying if there's like a 4, 6, 6, and a 4, you just make it 2, 3.
There you go. Small sum number ratio. Perfect. I like it. Any other questions on this? We're looking at number 2, C5H10 plus oxygen yields carbon dioxide and water. All right. Now, let me warn you, these look innocent. They look very, very innocent, but these are the ones that you really have to watch out for. And what I mean by that is, this is a type of reaction, you don't need to know what kind it is yet, but it's a combustion reaction, where the products are always carbon dioxide and water. Those are your only 2 products. These are the ones that will drive you nuts, I promise. Okay. However, there's 2 things that you may want to do to help eliminate that insanity. The first thing is, save balancing the oxygen for last. Okay? Don't even try to balance this until the very last step. Okay? Balance everybody else first, then worry about that last. Another thing, make sure that your coefficient for water is an even value. Okay? Say, like, for example, I need, and again, I'm going to pretend that I have a different number of hydrogens, but say I need 7 here to balance out the hydrogens. What's an even version of 7? 14, just double it, yeah. So we'll always want to have an even number there. If you have an odd number, I promise, it's going to be like a tennis match. You're just going to go back and forth, you're going to go nuts, you're going to be erasing. You better have a big eraser because you're never going to get the answer. The numbers are just going to get bigger and bigger. But if you have an even number here, life becomes a lot easier, and you save this for last. Okay? All right, so let's do the inventory. We have 5 of those, 10 of these, and 2 of those. You like that? Carbon, I've got 1, hydrogen 2, and oxygen 3 on the right side. Okay? All right. Now, normally what you would do is you would start with the carbon, but if you start with the carbon, you're going to have to erase something. So skip the carbon, go right for the hydrogen on a problem like this, okay, where you see carbon dioxide and water. So go for the hydrogen. So we have 10 hydrogen on the left side. How can we get 10 over here? Add a 5. Would you put a 5 there?
No.
Okay. So 5 is a good number, but it's not even. So double that. Trust me. This will keep you from pulling the hair out of your head. Okay? So yes, we want a 5 there, but if we put a 5 there, then that's really going to make our life rough. And here's the reason why. Because over here, I only have oxygen here, and it's even. No matter what number I put here, it's always going to be an even value. However, if I have an odd number here, that'll make my oxygens odd. So just double it. All right, so how many hydrogens do we now have? 20. How many oxygen do we have on the right side? 22, very good. So we have 10 times 1 plus 2. Okay.
Wait, 10 times 1 plus 2, that would be 12.
10 times 1, oh yeah, that'd be 12. Duh.
Sorry about that.
Let's go with 12 today. Alright, and so now let's fix our hydrogen on the left side. How can I get 20 hydrogen? Put a 2 there. So now how many carbons do I have? 10, and how many hydrogen? 20. Okay, so my hydrogens are looking good. Nice. How can I get 10 carbon? Put a 10 there. So now I've got 10 carbon. How many total oxygen do I now have on the right? 30. So I've got 10 times 2 plus 10 times 1. So 30. Okay. So my carbons are good, my hydrogens are good. How can I get 30 oxygen on the right or on the left?
15.
Good. Save it for last. Now, can these be reduced down any further? It's a small phone number ratio? No, maybe. No. If that were a 5, yeah, but it's a 2. So we'll leave it alone. Okay. So again, a couple things. Save the oxygen for last. Have an even value here. And actually, skip the carbon at first so you don't have to erase something. But that's not as big of an issue as these two here. Okay. Try number 3 on your own. Don't peek up here. The iron one. All right. Would everybody agree that's a good starting point?
I'm not done, Craig.
Well, I haven't done anything yet.
Well, I'm working, so
Okay, my bad.
How long have you been teaching chemistry?
God, too long. How old are you?
16.
Oh, 1 year less than you.
So 15 years. Do you like chemistry that much?
Too easy? What'd you have, Alyssa? Well, tell me how to work it. Let's do
Oh, I
that.
think I got it. What did you get?
So your irons are good, so skip that, right?
I did.
And then what'd you do for your copper?
No.
I put a 3 in front of that one.
Okay, good. Then what'd you do?
Yeah, no. He said even.
All right, well, let's do this. Our irons are good, the copper's good. How can we fix the phosphorus? 2 in front of here?
Yeah.
Okay. So that changes me to 2 phosphorus. How many oxygen do I now have? 8. And how many iron do I now have? 2. So everybody's good except for the iron. There you go.
Okay, yeah, I did do it.
Okay. All right, number 4. Another one of those combustion reactions. But look at those numbers. C12, H22, O3. Whew. Oxygen yields carbon dioxide and water. O5? Hope not. Oh, you mean there's 5 oxygens on the left?
Yeah.
Yes. In the inventory. Is that what you're saying?
Oh, you were just writing it down.
Yeah, I'm sorry. Alright, so there's our inventory. So, what do you guys want to do first? Hydrogen? Okay. So what should I put here? I'm looking for 22, so if I put a
22.
very good. Okay. Okay. Put an 11 there, then it gets interesting. So that gives us how many hydrogen? Nice. And how many oxygen do we now have on the right? 24, good. So 22 times 1 plus 2. Alrighty. So let's fix the other side. So how can I get 44 hydrogen? Put a 2 there. And now how many carbons do I have? 24. And oxygen on the left side? 8. Very good. Okay. How can I get 24 carbons? 24, yeah. So now I've got 24 carbon. How many total oxygen do I have on the right? 24 times 2 plus 22 times 1, which is 70. Very good. Okay. Now, we're ready for our oxygen, right?
Yeah.
However, we need 70 total oxygens on the left side, but we do have some hidden over here. How many do we have in this molecule?
6.
6. So what we need to do is do 70 minus 6 for this guy. So what is that? 64? And then divide that by 2, which is 32. Now, can that be reduced down?
Yes.
Yeah, and just do this. Just cross it off and reduce that way. And that's for any of them. Okay. And the reason why we can have an odd number of waters here is because we have an odd number to start off with. Okay. However, if you go even and then reduce, it makes it easier. Yeah, Caleb.
Why are we reducing the first place?
What's that?
Why are we reducing?
We want to make sure we have the smallest whole number ratio.
Okay, so if it's like got like, so it's kind of like square rooting a little bit. Like you're just taking it down to like the lowest it can go.
Yes, that's the best way to do it. Take a look at your homework. Which other one do you want me to do? I'll give you a hint. Don't pick any on the front side.
Can you do something on the back?
Yeah, pick one on the back.
Number 8, please.
Number 8? 8? Okay. That one's easy.
Choose one.
Can you pick like
Pick
a large
one.
on there? Pick a large.
Huh?
Hey, 15.
Let's do 16.
16? 17? 17's easy.
16.
16's easy. 15's a good one.
15.
That's
Let's
what I
go
said,
15.
the longest one.
Oh yeah, the longest one, 15.
Can we do 15?
We'll do 15. Alright, NH4Cl. Was that barium hydroxide? Yields barium chloride. Ammonia. Ammonia. And water. Alright. That's a good one.
No, it's not.
Yeah, that's a good one. Yeah. Alright, so let's write down nitrogen, hydrogen, chlorine, barium, oxygen. I think we've got a representative of each. So how many nitrogens do we have? 1. How many hydrogen? Nice. How many chlorine?
1.
Barium?
1.
Oxygen?
2.
Good, okay. Let's go in the same order here. And alright, so how many nitrogen?
1.
Hydrogen?
5.
5. Chlorine?
2.
Barium? 1. Oxygen? 1. Alright, now, here's something else that's really important. Before you start balancing, just kind of scan the equation and see if any of these appear in in a compound more than once. In other words, like I see hydrogen here, hydrogen here, hydrogen here, hydrogen here. So as a heads up, since hydrogen's in all but one of these compounds, save this for last. Okay, everybody hear what I said?
Yep.
So since you see an element appear in a lot of those compounds, save it for last. Just makes life easier. Because if you start to balance it here, then you're going to be really erasing a lot of things. So save something that appears in a lot of these last. So nitrogen looks good. Let's not mess with that. Skip the hydrogen. Go to the chlorine. We have 2 chlorines here, 1 chlorine here. How can we get 2 over here? Put a 2 there. So now that changes my nitrogen to 2. How many hydrogen do I now have? 10. Good. And how many chlorines do I now have? 2. Yeah. All right. So now my nitrogens have gone up. So how can I get 2 over here? Multiply that by 2. So I got 2 nitrogen. Now how many hydrogens do I have on the right? 2 times 3 plus 2, 8. Okay. And chlorines are good. Bariums are good. Ooh, oxygen. So how can I get 2 oxygen on the right side? Put a 2 there. So now I've got 2 oxygen. Now how many hydrogens do I have? 2 times 3 plus 2 times, what am I looking at? Hydrogen? Yeah, so 10. How we looking now? Isn't that cool?
Yeah.
So again, even though we didn't go out to seek hydrogen to balance out, it did it on its own.
So it's okay not to leave some of the blanks.
Yeah, in other words, if you need to put 1s there, that's fine. Yeah, if there's nothing in that blank, it's assumed to be 1.